A black hole is the universe's most effective prison. Nothing escapes, not matter, not light, not information. The event horizon is a one-way membrane. Cross it inward, and the laws of physics themselves forbid the return journey. That's the standard picture, and for a non-rotating black hole, it's correct. But most black holes in nature rotate, and a rotating black hole is a fundamentally different object, with a region outside its event horizon where space-time itself is so violently dragged into rotation that something remarkable becomes possible. You can take energy out, not by crossing the event horizon, not by any quantum tunneling or exotic process, by classical mechanics, by sending something in at the right angle, splitting it in the right place, and collecting what comes back carrying more energy than you put in. Roger Penrose described this in 1969. The mechanism is named for him, and the energy it extracts is real, physically sourced, and in a generalized electromagnetic form, almost certainly powering the most energetic phenomena in the observable universe right now. Let me show you how it works, and then let me show you what it means. Start with the geometry. Not all black holes are the same object. The textbook black hole, the Schwarzschild solution, found by Carl Schwarzschild in 1916, weeks after Einstein published general relativity, is non-rotating. It has a singularity at the center, an event horizon at the Schwarzschild radius, and perfect spherical symmetry. It is a clean, elegant, terrible object. In 1963, Roy Kerr solved Einstein's field equations for a rotating black hole. It took nearly 50 years after general relativity was published for anyone to find this solution. The mathematics is significantly more complex, and the physics it describes is genuinely stranger. A rotating black hole doesn't just curve spacetime, it drags it. The rotation of the black hole pulls the fabric of spacetime into rotation around it, like a spinning body in a thick fluid, except the fluid is space itself. This effect, frame dragging, exists around any rotating mass. Earth's rotation drags spacetime very slightly, an effect measured directly by gravity probe B in 2004. But near a Kerr black hole, frame dragging isn't a small correction. It's the dominant feature of the geometry, and it creates something that has no analogue in non-rotating spacetime, the ergosphere. The ergosphere is a region outside the event horizon, always outside, always escapable in principle, where the frame dragging is so extreme that no object can remain stationary relative to a distant observer. The spacetime is rotating faster than light relative to someone far away, and everything inside the ergosphere is carried with it. You can still move outward, you can still escape, but standing still is not an option. The geometry won't permit it. Between the ergosphere's outer boundary and the event horizon, that's the arena. That's where the Penrose process operates. Now I need to tell you about negative energy. Because this is the mechanism, and it's worth understanding precisely. In ordinary flat space-time, the energy of a moving particle, measured by any observer, is always positive. A particle moving forward in time, through normal space, has positive total energy. This is so fundamental it barely registers as a statement. It's just how energy works. Inside the ergosphere, it stops being true. Here's why. The energy of a particle isn't just about how fast it's moving. It's defined relative to a reference frame, specifically relative to the time coordinate of the spacetime. And inside the ergosphere, the time coordinate of a stationary distant observer is so twisted by the rotating geometry that some physically valid trajectories, some real paths through spacetime, have negative energy as measured in that frame. Not negative kinetic energy, negative total energy. The trajectory bends backward relative to the far observer's sense of time in such a way that the energy calculation returns a negative number. This isn't a violation of physics, it's a feature of curved rotating spacetime. The energy of a particle is always positive locally. To an observer right next to it, everything looks normal. The negativity is a global statement about how the trajectory relates to the distant reference frame, and the Penrose process uses this precisely. An object, a particle, a piece of matter, anything, enters the ergosphere. It's still outside the event horizon, it can still escape, but inside the ergosphere, while it's there, it splits into two pieces. This splitting is arranged, the geometry of the decay is chosen, so that one fragment follows a negative energy trajectory. That fragment falls into the event horizon. It crosses the point of no return, carrying its negative energy with it. The other fragment escapes. Now apply conservation of energy. The total energy is conserved. The escaping fragment's energy equals the original object's energy minus the energy of the infalling fragment. The infalling fragment has negative energy. Minus a negative number is plus. The escaping fragment carries more energy than the original object brought in. Where did the extra energy come from? The black hole. Specifically, from the black hole's rotation. When a negative energy object falls into the event horizon, it reduces the black hole's total angular momentum. The black hole spins slightly slower. That rotational kinetic energy, the energy of spacetime's rotation, is what the escaping fragment carries away. This is not energy from nothing. The black hole pays the bill. Every Penrose extraction slows the spin, slightly, of the Kerr black hole. How much can you extract? This is where general relativity gives a precise, beautiful answer. A Kerr black hole has two components of energy: the irreducible mass, the mass the black hole would have if all rotation were removed, and the rotational energy, which depends on how fast it's spinning. The Penrose process can access only the rotational component. For a maximally rotating Kerr black hole, spinning as fast as general relativity permits at what's called the extremal limit, the rotational energy is approximately 29% of the total mass energy. Of that, up to about 20.7% can, in principle, be extracted by the Penrose process. Let that number sit against some comparisons. Nuclear fission, uranium splitting, converts about 0.1% of mass to energy. That's what powers nuclear reactors and fission weapons. Hydrogen fusion, the process that keeps the sun burning for billions of years, converts about 0.7%. The Penrose process, from an extremal Kerr black hole, can reach 20.7%. It is the most energy-efficient process permitted by classical general relativity, by a factor of roughly 30 compared to fusion. As energy is extracted, the black hole's spin decreases. The ergosphere shrinks. A maximally spinning Kerr black hole, steadily drained by the Penrose process, approaches the Schwarzschild limit, non-rotating, spherically symmetric. At that point, the ergosphere disappears, the mechanism terminates. What remains can no longer be robbed. There is a deeper constraint underneath this, one that connects the Penrose process to black hole thermodynamics. Hawking and Penrose showed that in classical general relativity, the area of the event horizon cannot decrease. Every Penrose extraction is consistent with this. The infalling negative energy fragment adds to the event horizon area by more than the rotational energy removed. The extractable rotational energy is precisely the energy whose removal can occur without violating this area theorem. When you see the Penrose process constrained by the same area theorem that defines black hole entropy, you're looking at the edge of something we don't fully understand, a place where gravity, thermodynamics, and quantum mechanics all arrive at the same boundary from different directions. Now, does any of this actually happen? Is the Penrose process something that operates in the universe, or a theoretical possibility that remains a curiosity? In its original form, splitting a physical object inside the ergosphere, it's difficult to arrange in practice. The geometry is demanding, and astrophysical objects don't conveniently split on command. But in 1977, Roger Blandford and Znajek showed something more powerful. Magnetic fields threading through the ergosphere can extract rotational energy electromagnetically. The rotating spacetime winds up the magnetic field lines. The wound field launches plasma outward, two jets along the rotation axis, opposite directions. Relativistic, enormously energetic, continuous. This process, the Blandford-Znajek mechanism, doesn't require splitting objects inside the ergosphere. It uses the electromagnetic field as the intermediary, and it operates continuously as long as the black hole spins and magnetic fields are present. Both conditions are standard near accreting supermassive black holes. The relativistic jets you see emerging from active galactic nuclei, quasars, radio galaxies, blazars, jets that extend for thousands, sometimes millions of light years, carrying energies that dwarf entire galaxies. These are almost certainly powered by the Blandford-Znajek process, which is the electromagnetic generalization of what Penrose described. The first direct image of a black hole's shadow, M87 star, captured by the Event Horizon Telescope in 2019, showed a rotating supermassive black hole, 4 billion times the mass of the Sun, launching a jet extending 5,000 light years. The energy source of that jet, the rotation of the black hole, extracted through a mechanism rooted in the geometry Penrose identified in 1969. The Penrose process is not a thought experiment. It is operating right now in the centers of galaxies, including galaxies whose light is reaching us from billions of years ago. Step back from the mechanism and hold the geometry in mind. We define black holes as objects from which nothing escapes, and that's true, past the event horizon. But the ergosphere sits outside the event horizon, and inside the ergosphere, the rotating geometry stores energy, rotational energy of spacetime itself, that can be tapped, extracted, and carried away by the right interaction. Spacetime in general relativity is not a passive stage. It is a physical entity that curves, rotates, carries angular momentum, and can transfer that angular momentum to matter and fields. The Penrose process is one of the clearest demonstrations of this. Spacetime gives something up. Spacetime pays the energy bill. The universe contains supermassive black holes that have been spinning for billions of years, slowly yielding their rotational energy to jets that illuminate the cosmos. They are not simply consuming, they are also, in the precise sense Penrose identified, generating. The night sky is partly illuminated by energy that originated as the rotation of spacetime geometry around collapsed objects formed when the universe was young, and eventually, on timescales that make the current age of the universe look like an afternoon, every rotating black hole will be spun down. The ergosphere will contract to nothing. The Penrose mechanism will terminate. What remains will be a Schwarzschild black hole, silent, spherical, no ergosphere, no extractable rotational energy. Only the slow quantum evaporation of Hawking radiation over timescales so vast they resist any analogy. We speak of black holes as endings, and they are, but a Kerr black hole, for the duration of its spin, is also the universe's most efficient engine, a reservoir of rotational energy stored in the geometry of spacetime itself. Penrose showed that the most extreme object general relativity permits is not merely a sink, it is a reservoir, and one that geometry itself will eventually empty by rules we are only beginning to understand.